All right, so hopefully everything is working over here. I'll check the audio here in 1 second. But otherwise, everything looks like it should be going now. Last time we started looking at binary search trees. Actually, we were looking at them for quite a while here. And what we've done so far is we've done the search part of it, right? The binary search part of it is where we were searching through a tree. And the way that we did that is we started at the root, and using a comparator here, if that was the thing that we were looking for, then we returned that element. Otherwise, if the thing that we were looking for, the key element that we were given here, is less than the current element, then that means that we traverse left by going to the left child. Otherwise, we went to the right child there. And then ultimately, we return null here. Now, arguably here, I am making two calls to this compare function. And that compare function can actually be quite expensive. For example, when you did this with the sorting lab and you had locations, you could say that these two locations were the same if the city and the state and the zip and the latitude and the longitude, all 5 of those things were the same. You know, 5 total comparisons. And so it could be quite expensive to do that. In fact, it could be like that you are making an API call out to some Google thing where they are charging you by the call. And you don't want to do this twice, right? So what we should do is probably take this and put it into a variable, right? Not here, but here. Int result is equal to, I'm just going to compare it once. Ultimately, there's only really one comparison when you're doing this stuff, right? And the rest of it is simply just necessary for the control structure of the algorithm, right? So here we're going to actually have to switch it around, because if this is less than 0, then we need to go right? Because before what I was doing is I was going key, then current. This one is going current, then key. And so I've switched them around. And so the result here, result is going to be greater, right? You can go ahead and switch them around up here if you want to instead, and compare the key to the current. In which case, I should have just left it as less than. Right? I like that actually a little bit better, because it says that the key is less than the current element, and so therefore we need to go left. Right? I read left to right. I don't know about you. Right? In any case, let me make sure that that's working. Great. Right? So there's only really one comparison here. The elementary operation, if you were to analyze this, would be this comparison call right here. Okay? Unfortunately, we are not able to test it yet because I don't have a way to add things, right? And that's what we're going to do today, right? So let's go ahead and consider adding, say, add 49, right? So I'm going to have to search for where it should belong. I don't want to insert it up here, right? Instead, because if I tried to pigeonhole it in here, I would necessarily shove 50 somewhere else. And I don't want to do that. I want to have, at least as far as this tree is concerned, I don't want to mess up its trunk and its internal branches and stuff like that. Instead, when a tree grows, where does it grow in real life? It grows upwards. In other words, we're going to insert it as a new leaf down here. But now what about adding 49 here? I'll go ahead and say, well, if I'm going to add a leaf, then it should be on this side of the tree. So I'll come over here. If I'm going to add a leaf, it should be on this side of the tree. Right, so left, right, it should be on the right, and so I end up right here. Wait a second, 49 is already in there. Am I going to allow duplicates or not? So do you remember when we started this discussion? I don't know if we put it in there explicitly, but we said for our purposes we're only going to consider integers, and without loss of generality we'll assume that they're all keys, and that I guess we didn't put it in here, but we can go ahead and say that they're all distinct, right? To simplify, we will not allow duplicates. Right? Because what if you did allow duplicates, right? Then does it go left or right, right? So when you break ties, you're going to have to be consistent about it and always break it left or break it right, because you don't want to go one direction when you need to go to the other direction. So either you're going to have to make a choice, or you're going to have to say, wait a second, I'm not going to allow duplicates, because if you want duplicate, you are responsible for the comparator. So you're responsible for breaking ties. This person and this person, they have the same first name and the same last name. Does that mean that they're the same person? No, I would go and break ties then by the UUID or the social security number or the NUID. Something that is guaranteed to be unique and definitely not a duplicate, okay? If I've got a sale with the same number of elements, same number of items, exact same items, so everything has the same price, same taxes, but these are two different sales. How do I break ties? Through the code or something like that, right? In other words, there's always a way to break ties. Even if I have two people that are exactly the same, two instances in Java, say, where they have the exact same first name, last name, UUID, etc., I can break ties by looking at the memory address. Oh, that one comes first in memory, and that one comes second in memory, so therefore I can break a tie that way. Well, yeah, exactly. Right? So we are not going to allow ties. Right? So when I see 49 here, what should I do? Right? So at 1, find it. Find it. It or where it should be. Right? If duplicate, what should I do? It's not allowed, so I could do what? Oh, okay, return something. Return something. Right? If I wanted to throw a fit, though, I could throw it back at you as an exception, right? You tried to put something into this tree that's a duplicate, I'm going to throw it back to you. I don't like that too much, right? Because now having done 3 or 4 or 5 weeks now of JDBC, have you learned that checked exceptions are garbage, right? Having to surround every single thing that you do with this try catch for SQL exceptions just to rethrow them because there's no way that you can recover, I don't like that either. So I'm going to go ahead and return something, right? Return a flag value, right? To indicate you shouldn't have done that, but ultimately it's going to be a noop. Do you remember what noop or no-op stands for? No operation, right? Try to push something onto a full stack, no operation, or throw an exception. Try to pop something off of an empty stack, no operation or throw an exception, right? So we're going to have a no operation, okay? What if now I wanted to add something that does exist, say 86, okay? So again, what I'm going to do is I'm going to try to find where it should be. Well, 86, if it's going to be a leaf, it's going to have to go over here, go left, go right, and right there is where it should be, right? So I need to create a brand new node here with 86 in it and make it the right child of 85, okay? Let's go ahead and try to start doing that. Now, to try to start doing that, I'm going to steal this code right here. Get element or find element, because you have to find where it should be. So let's come over here, and that's where we'll start, okay? First of all, I'm going to immediately return a Boolean value right there. That's going to be my flag value. And let's document what this does. Inserts the given element into this binary search tree, right? If it is a duplicate, then it won't get inserted, and false will be returned. In other words, false. It does not have an effect on your list, or on your collection here. Otherwise, true code, true is returned on success. Right, there we go. So that's much better than a void function, because now I'm actually giving you information. Information that you can choose to ignore if you want to, or information that you can choose to use. Right? In either case, I'm not throwing it back at you as a checked exception or maybe an unchecked exception, forcing you to deal with it. Right? Now let's adapt this. I start at the root, and while the current is not null, then I compare it to the element. Right? It's no longer a key, it's the element and the current element. If you ever find a duplicate, what am I going to do? Return, as I did up here, false. As I documented up here, false. Otherwise, if the thing that you're trying to insert is less, then I go to the left child. Otherwise, I go to the right child. Right? And down here, I'll return true. Right? To do. Actually insert the new element. Right? Now I'll ask you, does this actually find where it needs to go? It finds close to where it needs to go. How do I break out of this while loop right here? When the current node, it becomes null. In other words, when I've fallen off the edge of this tree. Current is now pointing right here, in other words, to null. And because it's dot, 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 it doesn't exist yet. What do I actually need to make this a right child of 85? I need 85 right there. Right? So I need to keep track of two things. The current, and what would you call this one? It's parent, yes, but what would you call it as a variable? Previous. I like that. Previous. Why? Because I'm going to make previous's right child equal to this new node, and I'm going to make this new node's parent equal to previous to insert it just like I would with a linked list. Right? So let's go ahead and keep track of two things, a current and a previous. Previous. There we go. Initially that'll be null because there is no previous. Before I go down to the left, what should I do? Before I change current, I should change previous to be current. Right? I'm keeping track of two fingers, right? Now before current goes on to the next one, I need to make sure that previous is updated to that one, and then I can move this over. So I'm always moving these two things over down the tree. Right? A little bit of duplication there, but so be it. Right? Now let's actually insert the new element. So I need a tree node. Right? New leaf, right, is equal to new tree node of the element that I'm trying to insert. And I can easily set its new parent, new leaf dot set parent, to be the previous. Again, I can't do anything with current because I broke out of that loop. Current is null. Okay. I could have restructured this so that I didn't keep track of a previous and a current by simply just looking ahead. While you have a left child, while you have a right child, then descend down to it. Otherwise, break out of loop entirely. But I think that this version is much cleaner. Okay. So I've set the parent. Basically what I've done is I've done this, right? So let's choose a different color here, blue, right? I've set the parent of the current. So I've created that node, and it's now an actual node. I've set the parent. Now what I need to do is I need to set the right child of 85 to 86. What if instead I had inserted 84 though? I'd be over here instead. I need to make a distinction. Am I going to the left child or am I going to the right child? That means that I need to make one more comparison. Right? If the the element, here we go. I'll go with this comparison right here. In fact, I'll just steal all of that, right? I can't compare it to the current because the current is null again. So I compare it to the previous, right? And in fact, I'll put that into a variable here, right? Int result is equal to, there we go. Now I'm comparing the element that you're trying to insert element with the previous element. And so if the result is less than 0, you tell me, do I make it a left child or a right child? Else if result is greater than 0, I'll make it the other one, left child or right child. Else if result is 0. Right. So you start telling me what I do in each one of these blocks. First of all, this block. Should I even be writing that block? Why? That's a duplicate, right? I already took care of that. There is no way that I would be here at this point because I already returned false. So let's go ahead and get rid of that. So I'm comparing the element to the previous element. And that says that the element is less than the current element. So which direction do I go? Left child. Right? So previous dot set left child to new leaf. And by process of elimination, of course, set the right child and the right child. Now, another question, can I clean that up? Just make it else, exactly. Right. Simpler code is better code, okay? And now maybe I don't even want to put this into a result because I'm not even using that more than once. And so I will go ahead and put this over here, and if that's less than 0. The only reason that you would want to put it into an extra variable is if you're going to use that variable more than once. But I didn't, I just used it once because I cleaned all of this up. Right. Wonderful. Over here, let's go ahead and create a new binary search tree instead. And now we can start testing because Theoretically, we can get stuff in, we can pull stuff out. New binary search tree. And let's go ahead and change this from strings to integers because it's much easier to reason about. Right. Oh, I need a comparator. Good thing I've already put one together. Tree utils dot CMP. Right. How does that CMP int work? It's just a comparator for integers. A comparator for integers would have a compare method that takes two integers, a and b, s and t is what I've called them here. Probably better to call them a and b here. Right. And a and b. All I'm doing is comparing them to each other using their compare to method. This is going to be in ascending order. If I wanted to reverse the entire tree, and I wanted things that were larger over here and smaller over here, all I would need to do is what? Just reverse this. Positives become negatives, negatives become positives, zeros stay the same. And it still would have worked. All right, now that I've got my comparator, let's go ahead and insert some things. All right, add 10. Right. 20, or let's go ahead and go with 20, and then, I don't know, 5. Now, theoretically, what should that look like? 10, 20, and 5 before I run this. If I insert 10 into an initially empty tree, what should it look like? Just the root. Let's test that first. No pointer exception, right? Right at line 9. Why? So think about your linked list implementation. What was one of those corner cases you had to think about and be careful? If it was empty already. Do we have an empty tree here as of line 7? Yep. Did we think about that when we had this add method? Nope. So let's think about it now. If this root is null, then I know that it's empty, right? And so what's the special case there? This dot root is equal to new tree node of whatever elements in that element. Right? That's it. And then make sure that you return true because you actually had an effect on the tree. One other corner case or another issue that we were neglecting was what? Size. Initially, it's going to be 0. If we add something, then this dot size plus plus. This dot size plus plus here. No, we didn't end up adding anything. And then finally, this plus size plus plus. Okay. Let's see if that fixed our problem. Oh, okay. No news is good news. It works. Let's come back over here. Theoretically, what should it look like again? We're putting 10, 20, and 5. Where would 10 end up? Right there. Where would 5 end up? Right on that, right there. How do I know that it looks like that? Because I'm smart. Do I have any assurances? Well, let's go ahead and try to find the other ones, right? System.out.println, t.find, what do I call it? Get element, there we go. 10. So if 10 successfully got in there, it should find it and print out 10. If 20 got in there, it should find it and print out 20. If 5 got in there, it should print out 5, and it does. But do I know that the structure looks like that? There's no. In fact, let's go ahead and try another one here. Did I ever put in 15? So now, okay, that works. Right? But how do I know what the structure looks like? Let's go ahead and set the debug breakpoint, and let's go ahead and run the debugger. Right. I can take a look at it manually. Here's t. Here's the root. Right. The root has an element called 10. The root has a left child with an element of 5. The root has a right child with an element of 20. Looks kind of like that to me. All right, well, debugging wise, yeah, that looks good, right? But again, I would probably want to put this into a JUnit test suite and actually rigorously put this through through some stuff, right? So let's go ahead and stop this for now, and let me show you another way that you can do some ad hoc testing, right? I'd really like it if I could get it to look like that, right? If I had a visualization that, oh yeah, putting that stuff in that order resulted in this tree, right? How do you think I got this tree? Do you think I sat there and in some draw.io and made sure that everything lined up perfectly? No, right? What I did is I wrote some code to do this for me. And here we go. I think I need, oh no, I want to undo. Oh, come on. Oh, probably because that line is not commented out. There we go. Nope. All right, fine. Bye. There. So first of all, I've got a large BST here, binary search tree. I inserted things, I've got code here that simply inserts it in the following order: 50, 40, 60, 20, 45, and I'm adding each one of those things in turn by splitting them up. 50, 40, 60, 20, 45. That seems familiar. 50, 40, 60, 20, 45, 90. What ordering was this that we looked at with trees before? That's a breadth first search. All right. So inserting things in in this order, right, will result, at least for these numbers, will result in this tree here, right? Then I've got this other thing called Tutixi, right? So how many people have been using LaTeX for their design document? Probably zero, right? All right, do they talk about LaTeX in any other course? Like here, do your lab write-up in LaTeX. It's so much easier. Yes?
No, I haven't, but I wish I could.
Okay, all right. Well, here we go. I'm going to go ahead and show you what this code does. It produces a Tixi picture, right? And it's Tutixi, right? You could put it in a toString method or something like that. And let's go ahead and go to Tixi of T. There we go. And come on, what's wrong? Oh, I need to. It's not. I need to give it T. It's not an object-oriented. Come on, what's wrong? Oh, tree utils.toTixi. There we go. Right. And there's what that figure looks like, right? With just 10, 5, and 20 here. So let's actually go ahead and do it for the big tree. So tree utils dot, what was it? Big, large BST. There we go. Right. And it runs perfectly fine. And there's what it ultimately produces. Oh, wait, no. Let's get rid of that stuff first, because I don't want to find that stuff. Otherwise, it's a completely different tree. There we go. All right. So if you have used LaTeX? No? Nobody's used LaTeX? Okay. You can use an online tool called Overleaf, overleaf.com or whatever it is, right? And yeah, whatever. I'm not going to bother because I've already got it set up here on my Mac. Let me go ahead and get rid of that and show you what it looks like over here. So I've got a figure already. We'll walk through this here in a second. This is just one of those extra things that I like to mention. So we've got a happy little tree here. And here's what that Tixi image ends up looking like once you compile it, right? So this is LaTeX. Why do you want LaTeX? Because it's awesome for math, right? Do not even bother trying to write math in something like Word. Word is garbage for that stuff. In fact, if you're trying to do anything bibliography oriented, Word is garbage, right? The way that you do this in LaTeX is another tool called BibTeX, where you can just take the citation, put it into another file, and say, I want it as APA style. No, now I want it as APL style, or whatever styles are out there, right? And it automatically compiles everything for you, right? What does it look like? Well, there's my actual figure here, right? And it's got a bunch of bells and whistles too. You can make it larger, you can scale it up and down. You can change the level distance here, make it taller, right? You can make it wider, right? There we go. And that's a little bit bigger, right? That just spread the nodes out, and it spread out in both directions, right? Yeah, you can draw them instead of a circle. I don't know, square, or rectangle, right? And then I can say fill is equal to blue. Right? There we go. And now that's too dark. So I will go ahead and mix blue with 25% white. Right, there we go. There we go. Nice. Right. Steel blue is my favorite color when putting stuff up like this. Right. So that, and then you can define RGB colors and whatever. Right. So that's a nice way that you can do that. And here's some nice math. Right. If you want an integral, right, an integral from a to b of x squared dx. Right. Well, what's the? It's going to be. What is the integral of x squared? Is it? Well, yeah. Isn't it 3? It would be 2/3, right?
Oh,
Frac 2/3 of x cubed plus c. Go from a to b. Isn't that right? X cubed. Okay, 1/3. All right. You can write it like that with 1/3 out front, or you can take x cubed and put that on the top. There we go. Frac is, of course, a fraction. There we go. And then there's another way of getting that, right? I forget how to do it. Maybe it's like this. Okay, no, that's a vector now. Vertical line. I forget how to do a vertical line for that, but anyway, there you go. There's the indefinite integral, there's the definite integral, and then of course you can go ahead and just put in b cubed minus a cubed all over 3. Right? There's a summation. Do you remember what that's called? Gauss's formula. See, Gauss's formula 1, right? I was able to label this thing, right? So I can create an equation here, give it a label, and then later on I can make reference to that label, ref. Right? I can make a figure way down here, give it a label, figure, happy tree, and then I can make a reference to it up here. Right? There we go. See figure whatever for more information. Right? This is all markup, right? Markup language that, you know, I insert a figure here. Try doing that in Word, right? And now all your numbers are screwed up, right? There are ways of doing it automatically. I've never found them to actually work, right? Word is garbage. Right? Anyway, those are lots of things that you can do.
I think we were both wrong. I think it's x cubed divided by 5. So we're missing a constant of 1/2.
Oh,
Then 1/2 multiplied by 3 is a 5th.
all right.
I
So
don't know. It's irrelevant.
let's go ahead and get rid of it.
I like how it was 50 points for 2 + 1.
Yeah. Well, somebody was asking in another section how to, in fact, if you want to learn, if you wanted to do LaTeX and have some fun, I will go ahead and post the, if anybody asks for it, I'll post the source for assignment 8 due next week, the LaTeX source for it. Because somebody was asking about that, and I said, well, for that I actually use an exam class, right, instead of an article class. And when you do that, then you start labeling the actual questions, right? And the question here, once you begin the questions, you can say that question is worth 50 points, and it'll sum them all up automatically and create a rubric table for you. And then, of course, you can go ahead and put in solutions. Did you see the solution in the compiled version? I don't see a solution there. All right, I'm going to print out a key for all my TAs. All right. Print answers. There we go. Solution is 3. All right. So there are lots of really cool things like this. Like the user manual for Tixie alone for drawing stuff is like 3,000 pages. But most of them are examples and figures. Yeah.
So you don't like Word. How do you feel about Google Docs?
Slightly less annoying, but still just as annoying. Right? It's not. I would never write nobody writes. Nobody in the sciences writes anything in other than LaTeX for an academic paper. In fact, that's a litmus test. So there's a big, huge problem called P versus NP, and there's always some crackpot out there that claims to have, solved it one way or the other. And the first litmus test you can ask yourself is, did they write it in Word? If so, you can probably immediately dismiss it because no, there's probably no mathematical basis to it. It's not a serious article. So the reason I put that there, it was because it was a humble brag to the last section that I'm responsible for the complexity package. I wrote that 15 years ago as a grad student and added it to. So if you ever use the complexity package, that was me. And so I'm not famous. It typesets complexity classes like P and MP. Here it is. Right. Oh, say what?
What do you mean?
Well, this is deterministic polynomial time, and this is non-deterministic polynomial time. And so I just put all those together so that it was, and then there are options like caps, or you can change it from serif fonts to small caps fonts. What are the other options? I forget what. Yeah, something like that. Yeah, bold. We'll find out if that's an actual one. Good job. It was a long time ago, but
It's like I've dabbled in config files, but
okay. Yeah. And so the basic ones are defined there versus L. That's log space, UL, unambiguous log space, and you get all those. Right?
Do you get royalties from it?
So what?
Do you get royalties?
No, it's free and open source software. Yeah, it's released under an MIT license or something like that. All of my stuff for this course is released under a Creative Commons license, so you can't make money off of it, but you can use it however you want. Right? All right, so LaTeX, something to potentially learn if you want to go into, or if you want to do like really impressive, nice-looking lab reports or something like that. Right? Do be careful though, because I've seen instances in which people have written their math homework in LaTeX and they were like, "You must have cheated on this." It's like, no, I just know LaTeX. I did all my operations research, undergrad stuff in LaTeX.
It takes more time to look up. Can you make it professional looking?
Exactly. All right, so that is two basic operations. Let me get back over here. We have search, right, and we have insertion, right, and we are going to talk about deletion. In fact, we'll take the rest of the day here to talk about how to delete things, because it's not a simple matter. Let me go over here to something that looks nicer than what I just built. All right, so for example, what if I wanted to delete 48? Right? So, what's my first step? Find it. Right? So 1, find it. Right? If it's a leaf like this is there any problem with just deleting it by severing that connection right there? Nope.
Well, what if it's...
Okay, we'll get to it here in a second. But if it's just a leaf, are you going to kill your tree if you just cut off one leaf? No. Right? So just delete it. Now let's zoom in on that a little bit. Right? What does the leaf actually look like? It's got a parent up here, and here's the leaf. Right? We want to delete this guy right here. Remember that it has a reference back to the parent, and it has a reference, that parent has a reference to it. So one, we need to distinguish, is it a left child or a right child, because we want to delete the right one. Right? But if we've got that node, then we can always jump to the parent and ask, is my child, am I a left child or am I a right child? Right? In which case I can then sever that connection. Technically, you should sever this connection, but do you need to? Once this connection is severed right here, can you ever get back down to there? No, so you could go ahead and ignore that. Now, if you were in a programming language like C or C++ and you were doing this and you had two references, one way or the other, yeah, you do have to sever them both. Why? Because severing this will make it, in Java, will make it eligible for garbage collection, and the garbage collector will automatically clean it up for you, right? But in C, you have to sever both of those connections and then manually free this up with a destructor or free. Right? If it's destructor if it's C++, free if it's C. Right? So it's not just a simple matter of delete it, it's also make sure that you're taking care of these references. All right, what if it's not a leaf? What if it's, say, 60? Right? So, first of all, find it. Right? Now, to delete 60, just zoom in on this. Right? Only look at those 3 nodes. What is it because it only has one child, right? There's one child. If one child, then we have a situation like this before. If you just zoom in on this, you want to sever both of these connections, and you want to make it look like this. What does that look like? If you ignore everything else around it, looks like a linked list to me. Right? And we know how to do that. Right? All you have to do is get rid of that, and then we make sure to fix it like that. Right? Now, if I were to redraw this tree, of course I would take this subtree right here and I would move it up, because this is of depth 0 and this is of depth 1. So I would end up taking this thing and moving it up just slightly to visualize it. Right? But if it's one child, then that's fine. You promote the single child. Right? And you do a reference shuffle just like you would a linked list. Okay? All right. Well, that's all well and good if it has no children, a leaf, one child, either left or right, but what if both children? If 2 children? For example, let's now go ahead and delete 50 instead. Right. Yeah, delete the root.
That would kill the tree.
Definitely, right? So I don't want to just, yeah, let's go ahead and get rid of it all. If I just deleted it like that, of course it would kill the tree. But do I have a tree anymore?
No.
I have 2 trees. I have a
Dead
forest, right? 2 dead trees, exactly. So I don't want to do that. I don't want to cause any harm to the tree. So what I'm going to do is I'm going to prune it by simply taking out something lower in the tree, higher in the tree, right? You don't want to cut off big branches at the trunk. You want to cut off little branches at the top. So what I mean by that is, let's go ahead and delete 50. Right? That leaves a gap. Right? What could I fill into that gap that would be valid? I could take this and move it up here, but then I'd just be shuffling the problem, right? Now, okay, now I can go ahead and promote this. I can promote this. Eventually, I'm going to get into trouble.
Right. 45, 49, 48.
Yeah, exactly. So it would violate the binary search tree property. Let's focus on the left subtree over here. Give me a value here that I could take out and put up here as the root and still have everything over here less than it. All right, why did you immediately jump to 49? Yeah, it's the largest among the less elements. So 49 up here. Right? So I could either A, promote the largest in the left. If I had asked you to focus on the right subtree, which one would you do then instead? The smallest, which would be 60. Right? So the or the smallest in the right. Right? Okay. That, however, also just shifts the problem. Right? 49 is now gone. Is that a problem though? What can we do with its child there? Move it up. In fact, I'm not going to draw it like that, but I'll draw it like this. There we go. Right. Why was I able to do that? Because it only had one child. What if that was not the case? Right? So I've got here's the largest. Also, let's go ahead and simplify that. I'll call it the max. Right? It's the maximum element in the left subtree. I came down here and I found the maximum. Suppose it has a left child and suppose it has a right child.
Oh, no, the right would be the new max.
Bingo. This cannot happen.
I
Why?
could have a left child.
Because the max is less than the right. So this wasn't the max. This was the max. So the max is never going to have a right child, right? And you fall back to either this case, or if it had no children, then and it was a leaf, then you're done, right? How do I find the max? If I just start at a table, at a tree here, right? Here's a big giant tree. Come on, there we go. Here's the root. Ah, I don't know how to shut that off. All right. Here's the root. Where's the max going to be? It's definitely going to be at the bottom, but how do I find the max? So yeah, do I search the entire tree though? No. Where's all? What do I need to do? Just keep going right. There's the max right there. Come over, yeah. Well, of just any tree. Right. So if I start here and I just keep going right, I find the max here. If I started here and wanted to find the max of this subtree, I would do the same. Just keep going right until you can go right no further. What if you wanted to find the min? Go all the way left. There it is. All right. So now we won't actually program this. It's weird. Okay. All right. Anyway, the stuff's popping up over here. Oh, maybe OBS, maybe something else. But in any case, we won't actually be programming this. I'll leave that as an exercise if you want to do it. Actually, I think it's in your lab this week that we do it for you. But in any case, what I want to do is I want to show you something else. Right? Remember that I told you that the binary search tree can be degenerate? In fact, let me show you a degenerate case here. Right? New binary search tree, new. Right? And what I'm going to do is I'm going to, for int equals 10, I is less than or equal to 100, I plus equals 10. Plus equals, there we go. T dot add I. What is that going to look like? I plus equals, there we go.
It's going to be like 10.
Tree utils dot, there we go. All right. It's going to be 10, 20, 30, 40, 50, all the way up to 100. But what is it physically going to look like if I wanted to compile this? Let's go ahead and replace this tree right here. There we go. What does that look like to you? A linked list. What's the depth of that? There's 10 elements in there, so the depth is 9. In other words, the depth is order n. It's no better than a linked list. We're about right back at square one. Right? Exactly. Have a little twig or something. Right? So remember, the whole reason that we wanted to look at trees is because we could potentially exploit the structure. If we have a full or nearly full binary search tree, then we would have a guarantee on its depth, but we don't. Right? Instead, all operations could be efficient if we did something like this, but we're not going to be there. We're not going to get there. I'm going to show you a preview of something that you might see in CS3. I might have seen this. Have you seen this before? The hill? No? Okay. So let's look at the hill analogy. Let's look at an unbalanced binary search tree. Right? What I want you to do is I want you to imagine that this is actually a chain on top of a hill, and that there's this guy on the other side, and he's going to pull that chain over the hill. It ends up being a rotation, right? This is a left rotation or a counterclockwise rotation. What ends up happening is that 20 is now at the top of the hill, 10 has now gone over to the guy, and 30 here now has been pulled to the foot of the other hill. This is a balanced binary search tree. Right? What if it were the other way? Well, the guy would just stand on this side instead and pull this way instead. That would be a right rotation. What if it were zigzaggy? Right? So here is 10, and then over here is 30, and then over here is 20. I need to get it to look like this. So what I'll do is I'll do 2 rotations. Here's a hill right here where I rotate it right. Here's another hill over here where I rotate it left. The first time that I do this, I end up with 10, 20, 30, which is exactly what was up here. Right? And then I rotate it again on the left, which gives me this guy right here. That's called an AVL tree. It has left-right rotations, right-left rotations, 4 different types of rotations. That's only one type of balanced binary search tree. There are also B trees, which are used in your databases. There are red-black trees, which is the actual implementation in Java. There are, at least a dozen other implementations that people have come up with that basically reorganize themselves so that it is a balanced binary search tree, giving you a guarantee on the depth. We're not going to get there. Instead, what I'm going to give you is something else. Something that looks like this. Freeze, where are you? Heap. There we go. Come on, there. This is called a min heap. Oops. It's a min heap. Right? And it satisfies 2 properties. First of all, it's full. Right? Why is it full? Look at every level. Every single node is present except for the last level. But what can you tell me about that? They're all shoved to the left, right? So it would be wrong if I had something like this sitting off the side here, right? There's a gap. That gap is bad. That is not full, right? So what you have is a fullness property, okay? And 2, you have the heap property. First of all, is this a binary search tree? Is everything over here less than 1? Certainly not. Is everything over here greater than 1? Certainly not. Right? Instead, what can you say about this node?
Greater than one on the right side?
Say what?
Said it is greater than one on the right side. But
Everything is greater than. Oh, I guess yes. That would be true. Right? But that's just because of the heap property. What is the heap property? Look at this node right here. Tell me about both of its children. It's greater than this key value.
Oh, no, yeah.
Pick any node. 50. Its 2 children, 60, 53, are greater than it. So the heap property is that for a node K, both its children are greater. And once again, we can go ahead and just assume that they're all integers. You can assume that they're all unique, no duplicates, whatever you want to assume about it, right? So these 2 things together mean that we've got a tree with depth being order logarithmic, right? Now, you can't do the general CRUD, create, retrieve, update, and destroy, right? Why? Because how do you search? Find me 70, right? Can you say that 70 is in that section or that section? Nope. I mean, you can tell it right here, but programmatically, could you do that? Nope. In order to find 70, what would you have to do? Traverse the whole tree, potentially, right? In order to find, say, 75, which is not even in here, right? You'd have to say, that's not it, that's not it, that's not it. Maybe do a BFS, right? Nope, it didn't exist. You'd have to find it, right? So you're not going to have general purpose data structure out of this thing. But what can you find very, very easily? The min, right? So where is the minimum? Get min, right? It's always at the root. Okay? Cool. What's another thing you can do? Well, eventually we're going to want to add stuff. Add element, right? Add a new element to the heap, right? Both of these are going to be order D, but because of this fullness property, and D is logarithmic, both of these can be done in order log n. So I could put stuff in, I could take stuff out, and I could guarantee you that it's all going to be efficient. Right? The problem is, how do we do it? Right? In fact, this is another restricted access data structure. Yeah, you can go ahead and search for whatever element you want, but it's going to be linear, right? You can BFS, pre-order traversal, in-order traversal, whatever traversal you want to do, it's going to be linear. It's not going to be logarithmic. I'm going to restrict your access to these two basic functions. When I do that, then I can guarantee you that you're going to have log n. Right? All right, what about getting the minimum here? Well, first of all, I can say that temp is going to be the root element. Well, no, the minimum is always going to be here by the heap property, right? Because both of its children are greater. Its children have descendants that are greater. It's always going to be greater. Where's the maximum going to be? Somewhere at the very bottom, right? It could be over here or it could be over here. I don't know which. It depends on the topology of the tree. Right? But we're not trying to find the maximum. We're trying to find the minimum. So I'm going to save that off into a temporary variable, and unfortunately that leaves a gap. Okay. Now with a binary search tree, we had a nice way of fixing this gap, right? By finding the maximum. Can you do that? And in fact, putting the maximum here, would that be even appropriate for a heap? Nope. You want to put something that's smaller. Okay. So let's look at its two children first of all, 5 and 30. Which one could I put up there? 5. Okay. That means that now I've got a gap there. Which one of those children could I put up? 50. Okay. That means that there's a gap right there. Which one of those children could I put up? 53. Okay. That means that there's now a gap down there. Careful. Is that full anymore? Nope. There's a little gap right there. Fail. Back to the drawing board. Right. Once again, I am going to get rid of 1 there, but there's a gap. Let's focus on the fullness property first. Which one of these guys could I take and put up at the top and still have the entire tree be full? The heap property won't be satisfied, but at least the fullness property will be satisfied. 63. Why? It's the last one. It's at the bottom level, and it's the rightmost node. So what I can do is I can take 63 and put that up here, right? And I can erase that entire thing right there. There. Okay? It's still full. But the heap property is no longer satisfied. So let's fix it. It's called heapify or fix heap, right? I need to do something with one of its two children, right? Now, same process as before. Which one could I swap it with so that the heap property would be satisfied at least with these 3? 5. Okay. So this becomes 5 and this becomes 63. There we go. Okay. So this is now 63, right? Is the heap property satisfied now? Nope, because 63 is greater than 50 and it's greater than 55. So which one of those guys should I promote and swap with?
55.
Careful.
Oh, never mind.
50, right? So 50 now, and then this becomes, what was it, 63? Right, there we go. All good? All right, so is the heap property satisfied now? Nope, not yet. 53 needs to be promoted up. There we go, 53. Now is the heap property satisfied? And it's full, right? So all I need to do is find this last guy up here, swap him out, making sure that I save this guy over here because I'm going to return him, get min, right? I want you to get and remove the minimum. And then I just need to heapify it down, fix it down. Right? The fullness property is still satisfied. The heap property is still satisfied. It is still a heap. And guess what? Heapifying it downward is all going to be order D. And because of fullness property, it's going to be order log n. Right? Perfect. All right. What about inserting something? I want to add an element. So now if this were a physical heap, right? Like a heap of garbage or a heap of clothes. And you threw something, it's a heap of garbage, and you threw something on top of it. Is it going to end up on the top?
Do something.
Not, you could, right? But usually if it's a big giant pile, right, what's going to happen if you throw something on the top? It's going to come down. Is it going to go all the way to the bottom? Not necessarily, right? Right? So if I tried to do something like that here, right? Let me go ahead and insert, I don't know, 45. Is 45 in there? Yeah, 45 is in there. I don't know, 42? That's probably my go-to. That's why I never put 42 in anything, because I always remember, oh, you just use 42. Right? All right, so if I tried to come in here like a binary search tree and treat it like a binary search tree, right? Well, I'd say, oh, 45 doesn't belong there because 1 needs to stay at the top. So do I traverse left or do I traverse right? Is there any information as far as these 3 nodes are concerned to tell me where I should put it? No. What if I went, oh, well, 42 is large. I'll go ahead and do it with the smallest one. Right? I'll go down to the smallest one here, go down to the smallest one here, go down to the smallest one here, and oh, okay, I could go ahead. I got lucky there. What if my criteria were different though? Right? What if it was the largest one, 30, right? And the largest one, and then the largest one? And okay, do I put it as a left child or right child? There's a huge gap here now. Right? There is no way for me to tell if I'm standing on this one node here, right, that I should go left or I should go right. So I'm going to look ahead. I'm not going to start at the top. I'm going to start at the bottom. Where could I put 42 so that the fullness property is satisfied? Right here as the left child of 53. Now be careful. Is the heap property satisfied? Nope. Same trick as before, but instead of going from top to bottom, I go up. Right? So 42 and 53 are out of order. Okay? Swap them. 53 and 42. 42 and 50 are out of order, so swap those. Now, what about 5 and 42? They're good. In other words, I was able to stop short. I didn't need to go all the way up. If I had inserted 0, or say -1, right, then yeah, I would have needed to heapify all the way up. But I don't go any further than the root node. In other words, it's still going to be order D, which, because of the fullness property, is going to be order log n. All right, we'll look at that in a little bit more detail next time and look at maybe a couple of implementations. But otherwise, ultimately, what we're going to do is we're going to use it next time in our last algorithm that we're going to look at, heap sort. Right? Why? Because it exemplifies everything about this course. Smart data structures and dumb code are a lot better than the other way around. How can I use this fact that I can get the min efficiently? If I got the min, then got the next min, then got the next min, then got the next min, what would the ordering be? Sorted, right? So all I have to do is use this data structure, throw stuff into it, and pull stuff out of it, and guess what? It's sorted. All right, we'll look at that next time. All right, I'll see you upstairs then.